The night sky holds secrets written in light that has traveled billions of years to reach us. When astronomers turn the James Webb Space Telescope toward the farthest reaches of observable space, they expected to uncover mysteries about the early universe. What they discovered instead has shaken the foundations of modern cosmology and forced scientists to reconsider everything they thought they knew about the formation of the largest objects in the cosmos. In the ancient galaxy designated UHC-1, located so far away that we see it as it existed just for 170 million years after the Big Bang, researchers found something that should not exist. At the heart of this primordial galaxy sits a black hole with a mass 40 million times that of our Sun. To put this in perspective, the black hole at the center of our own Milky Way galaxy, Sagittarius a star, which has had nearly 14 billion years to grow, weighs in at approximately 4 million solar masses. The black hole in UHC-1 is 10 times more massive, yet it existed when the universe was barely 3% of its current age. This discovery is not an isolated anomaly. Since the James Webb Space Telescope began operations, it has been systematically detecting supermassive black holes throughout the early universe that defy conventional explanation. These gravitational behemoths appear to have reached masses equivalent to millions or even billions of suns during an epoch when, according to our best theoretical models, they should not yet exist. The problem is not merely that these black holes are unexpectedly large. The fundamental issue is that we cannot explain how they grew so massive so quickly. For decades, the prevailing theory held that supermassive black holes form through a relatively straightforward process. A massive star would reach the end of its life cycle and collapse, creating a stellar mass black hole perhaps 10 to 100 times the mass of the Sun, over vast stretches of cosmic time. These modest black holes would gradually accumulate mass by consuming surrounding gas and dust, and by merging with other black holes they encountered. Through this patient accumulation spanning billions of years, they would eventually grow into the supermassive black holes we observe at the centers of modern galaxies. This traditional model works perfectly well for explaining the black holes we see in the present-day universe. But the James Webb Space Telescope has revealed that the early universe was already populated with black holes that had somehow bypassed this slow growth process entirely. These ancient monsters had achieved colossal masses at a time when the universe itself was still in its infancy, leaving astronomers scrambling to explain what they were seeing. Roberto Maiolino, an astrophysicist at the University of Cambridge who has been studying these objects, described the current state of the field as a revolution in understanding. The discoveries being made are not minor corrections to existing theories but fundamental challenges that require reimagining how the universe's largest structures came into being. Research teams around the world are now racing to develop new models that can account for what the telescope is revealing, and the implications extend far beyond black hole physics alone. Cosmic timeline. To understand why these early black holes present such a profound challenge, we need to trace the history of the universe from its beginning. The Big Bang occurred approximately 13.8 billion years ago, initiating the expansion of space itself along with all the matter and energy the universe contains. In the first few moments after the Big Bang, the universe was unimaginably hot and dense, filled with a seething plasma of fundamental particles. As space expanded, temperatures dropped, allowing these particles to combine into the first atomic nuclei. For roughly 380,000 years, the universe remained opaque to light. It was too hot and dense for photons to travel freely. They would scatter off free electrons after traveling only short distances. This period is sometimes called the Cosmic Dark Ages, though not because the universe was literally dark. Rather, it was a time when light could not travel far enough to illuminate anything. Then, around 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons to be captured by atomic nuclei, forming the first complete atoms. This transition made the cosmos transparent for the first time, allowing light to travel freely across vast distances. The light from this epoch still reaches us today as the cosmic microwave background radiation, a faint glow visible in all directions that represents our deepest view into cosmic history using CO1V and TIONAL electromagnetic radiation. When astronomers study this ancient light, they find remarkable uniformity. The early universe was extraordinarily smooth, with matter distributed almost evenly in all directions. There were tiny variations in density from place to place, fluctuations that would eventually see the formation of galaxies. But these differences amounted to only about 1 part in 100,000 following the era. When the cosmic microwave background was emitted, the universe entered a true dark age. No stars yet existed, and the glow from the Big Bang itself was fading as the universe expanded and cooled for perhaps the next 200 million years. The cosmos was filled with vast clouds of neutral hydrogen and helium, the only elements that existed in significant quantities. These clouds drifted through an expanding void, slowly being drawn together by gravity, where the density fluctuations from the Big Bang had left regions slightly denser than their surroundings. Current models suggest that the first stars began forming somewhere between 100 and 300 million years after the Big Bang. These were not stars like our Sun, known as population 3 stars. They were composed entirely of hydrogen and helium with only trace amounts of lithium. With no heavier elements to radiate energy efficiently, these primordial stars had to be extraordinarily massive to achieve the temperatures and pressures needed for nuclear fusion. Theoretical calculations suggest they may have been 30 to 300 times as massive as our Sun, burning with furious intensity but living for only a few million years before exploding as supernovae. When these first stars detonated, they forged heavier elements in their cores and scattered them into space. This began the process of chemical enrichment that would eventually lead to planets, life, and the complex chemistry we see in the modern universe. The explosions of these massive stars also left behind remnants, neutron stars in some cases, but more commonly, stellar mass black holes ranging from perhaps 10 to several hundred solar masses, according to traditional models. These stellar remnants were the seeds from which supermassive black holes would eventually grow. Stellar mass black hole could attract gas and dust from its surroundings, gradually increasing in mass. When two black holes encountered each other, they could merge, combining their masses. Over hundreds of millions or billions of years, through countless such events, modest black holes might grow into genuine giants. But there is a fundamental speed limit on this growth process, and that limit is what makes the James Webb discoveries so puzzling. When a black hole consumes matter, that material does not simply fall straight in. Instead, it forms a swirling disk of material orbiting the black hole, gradually spiraling inward. As the material in this accretion disk gets compressed and heated, it radiates enormous amounts of energy. This radiation exerts an outward pressure on any additional material trying to fall toward the black hole. There exists a balance point where the inward pull of gravity exactly matches the outward push of radiation pressure. This balance point defines what physicists call the Eddington limit, named after British astronomer Arthur Eddington, who first described it. When a black hole is feeding at its Eddington limit, it is growing as rapidly as the laws of physics will allow while still behaving in accordance with this balance between gravity and radiation. If it tried to consume matter faster, the radiation pressure would blow away additional material before it could fall in. For a stellar mass black hole of perhaps 100 solar masses, growing at its Eddington limit, reaching a mass of 1 million suns would take several hundred million years. To reach a billion solar masses would require more than a billion years of continuous feeding at maximum efficiency. These timescales work fine for explaining the supermassive black holes we see in galaxies that formed billions of years ago. But they cannot explain black holes with masses of millions or billions of suns existing just a few hundred million years after the Big Bang. The black hole in UHC-1, with its 40 million solar masses at an age of only 470 million years, exemplifies this problem. Even if a stellar mass black hole of 100 suns formed immediately after the first stars appeared around 200 million years ago, it would have had at most 270 million years to grow before the time we observe UHC-1. Growing to 40 million solar masses in that time frame would require feeding at more than 100 times the Eddington limit continuously for the entire period. This is not merely implausible, it violates our understanding of how accretion onto black holes works. The situation becomes even more extreme with some of the other objects James Webb has detected. Black holes with masses approaching or exceeding 1 billion suns have been spotted in galaxies existing less than 1 billion years after the Big Bang. For these objects, no growth scenario starting from stellar mass seeds can possibly work, even with the most optimistic assumptions. The universe simply was not old enough for conventional growth processes to build such monsters. From stellar origins, a galaxy that challenges the models among the most studied of these problematic objects is the galaxy designated GNZ11, one of the most distant galaxies ever observed. Light from GNZ11 has been traveling for more than 13.4 billion years to reach us, meaning we see this galaxy as it existed just for 100 million years after the Big Bang. When the Hubble Space Telescope first detected GNZ11, it was remarkable simply for being so ancient and so bright. But when James Webb turned its far more sensitive infrared instruments toward this distant galaxy, it revealed something even more extraordinary. At the center of GNZ11 sits a black hole estimated to have a mass around 2 million times that of our Sun. While this is smaller than the 40 million solar mass black hole in UHC1, GNZ11's black hole existed at an even earlier time. The galaxy also exhibits other unusual properties that provide clues about the extreme environment surrounding this ancient black hole. Webb's spectroscopic observations detected gas moving at velocities exceeding 1,700 kilometers per second near the galaxy's center, indicating powerful winds being driven by the black hole's accretion activity. The data also revealed unusual chemical signatures. While population 3 stars should have been composed almost entirely of hydrogen and helium, the gas in GNZ11 shows evidence of heavier elements like carbon, nitrogen, and oxygen. This indicates that multiple generations of stars had already lived and died in this galaxy, even at this extraordinarily early epoch. The presence of these heavy elements, combined with the signatures of the central black hole, paints a picture of a galaxy that was evolving at a furious pace in the early universe. Perhaps most intriguingly, researchers have suggested that GNZ11 might provide evidence for an entirely different formation mechanism for early black holes. Rather than growing from stellar mass seeds, some theories propose that certain black holes might have formed through the direct collapse of massive gas clouds in the early universe. These direct collapse black holes could have been born with masses of thousands or even millions of suns, giving them a tremendous head start over their stellar mass cousins. The concept of direct collapse requires very specific conditions, and in the early universe, there were regions where clouds of primordial gas remained unusually pristine, uncontaminated by the heavy elements produced by earlier generations of stars. In these metal-free environments, the gas could not cool efficiently. Normal star formation requires gas to cool and fragment into smaller clouds that collapse to form individual stars. Without efficient cooling, an entire massive gas cloud might instead collapse as a single entity, creating either a supermassive star or perhaps directly forming a black hole. For direct collapse to work, the gas cloud also needs to avoid fragmenting due to its own angular momentum. In most regions of space, clouds of gas are rotating, and this rotation tends to cause them to break apart rather than collapse wholesale. But if a gas cloud is bathed in intense ultraviolet radiation from nearby sources, this radiation can heat the gas and inhibit fragmentation. Under these rare but plausible conditions, the gas cloud containing perhaps millions of solar masses might collapse directly into a massive black hole. One recent study has proposed that GNZ11's central black hole might have originated from the merger of multiple primordial black holes. Primordial black holes are a hypothetical class of objects that might have formed in the first fraction of a second after the Big Bang, when density fluctuations in the expanding universe could have created regions dense enough to collapse immediately into black holes. These primordial black holes could come in a wide range of masses, if they existed and if they tended to congregate in the regions where early galaxies were forming. Their mergers might have created the massive seed black holes that grew into the giants we now observe. While individual objects like UHC1 and GNZ11 have captured significant attention, some of the most puzzling discoveries from James Webb involve a population of strange objects dubbed little red dots. When astronomers first began processing images from Webb's deep surveys of the early universe, they noticed numerous compact, extremely red sources scattered throughout their fields of view. These objects appeared primarily in observations of the universe as it existed between about 500 million and 1.5 billion years after the Big Bang. The red color of these objects indicates that their light has been dramatically redshifted by the expansion of the universe during its long journey to reach us. But beyond that basic observation, little red dots initially defied easy categorization. They were too compact and too bright to be typical galaxies from that era. Early speculation suggested they might be galaxies that had somehow grown far larger than should have been possible in the available time, leading some researchers to call them universe breakers for their apparent violation of cosmological models. As data accumulated and analysis techniques improved, a different picture began to emerge. Rather than impossibly large galaxies, these little red dots appeared to be something perhaps even more remarkable: supermassive black holes in their youth, caught in a peculiar stage of their evolution that had never been directly observed before. The key evidence came from detailed spectroscopic observations that could break down the light from these objects into its component wavelengths, revealing signatures of their physical composition and the processes generating their light. One intensively studied little red dot is an object designated XO1, observed as it existed roughly 700 million years after the Big Bang. Astronomers have used a technique involving the motion of gas around the central object to estimate its mass. Gas orbiting a massive object moves at speeds determined by the gravitational pull it experiences. By measuring these velocities using the Doppler shift of spectral lines, researchers can infer the mass of the central body. For QSO1, this analysis indicates a black hole mass of approximately 50 million suns. What makes QSO1 particularly perplexing is the apparent absence of a substantial galaxy around the black hole. In the modern universe, supermassive black holes reside in the centers of galaxies, surrounded by hundreds of billions of stars. The black hole's mass is typically only about 1,000th of the total stellar mass of the galaxy. But for XO1, researchers have struggled to find evidence of significant stellar populations. The observed light appears to come almost entirely from the vicinity of the black hole itself, with very little contribution from surrounding stars. Lucas Furtick, an astronomer at the University of Texas at Austin who has studied XO1, noted that despite intensive searches, the host galaxy remains essentially invisible. The observations show a massive black hole apparently existing in isolation or surrounded by it. Most a very modest stellar population, this discovery challenges conventional understanding of how galaxies and their central black holes co-evolve. In standard models, galaxies form first, and black holes grow within them. But QSO1 suggests a scenario where the black hole might have formed first, with the galaxy assembling around it later. Another intriguing little red dot has been nicknamed the cliff based on an unusual feature in its spectrum. When astronomers examined the wavelength distribution of light from this object, they found an extremely sharp jump in brightness at a specific wavelength corresponding to hydrogen emission. This distinctive signature suggests the presence of a dense cocoon of hydrogen gas surrounding the central black hole, heated to a particular temperature by the intense radiation emanating from the black hole's accretion disk. The properties of the cliff match theoretical predictions for a long hypothesized but never confirmed type of object known as a quasi-star or black hole star. In this scenario, a massive black hole sits at the center of an enormous envelope of gas. The gas is heated by the black hole's radiation, causing it to glow, but the black hole itself remains hidden within this cocoon. From the outside, such an object would appear somewhat star-like, despite being something entirely different, a supermassive black hole wrapped in a stellar-scale atmosphere. The quasi-star concept offers a potential explanation for how supermassive black holes could have grown so rapidly in the early universe. In this model, a direct collapse process creates a massive black hole surrounded by a substantial reservoir of gas. Rather than the black hole immediately expelling this material through radiation pressure, the gas forms a quasi-stable envelope. The black hole feeds on this envelope from the inside, growing rapidly while remaining shrouded. Eventually, after perhaps a few million years, the envelope is either consumed or blown away, revealing a much larger black hole than started the process. In January 2026, A major study published in the journal Nature provided strong evidence that many of the little red dots are indeed young supermassive black holes in a cocoon phase of their evolution. The research team, led by scientists from the University of Copenhagen, analyzed high-quality spectra obtained by James Webb of multiple little red dots. They found that these objects share common characteristics consistent with black holes surrounded by dense ionized gas. The black holes appear to be feeding at rates approaching or even exceeding their Eddington limits, growing rapidly while enshrouded in the material they are consuming. This cocoon phase model has gained substantial support within the astronomical community because it elegantly explains several puzzling features of little red dots. Their compact appearance makes sense if most of the light comes from a relatively small region around a hidden black hole. Their unusual spectra can be understood as emission from ionized gas at specific densities and temperatures. And their sheer numbers suggest they represent a common, albeit brief, phase that many early supermassive black holes pass through. Among the most dramatic discoveries enabled by James Webb is an object catalogued as LID 568, a black hole that appears to be violating what scientists thought were fundamental limits on growth rates. LID 568 exists at a time approximately 1.5 billion years after the Big Bang, which, while still early in cosmic history, is considerably later than objects like UHZ-1 or GNZ-11. What makes LID 568 extraordinary is not its age but the rate at which it appears to be consuming matter. Detailed analysis of LID 568's spectrum reveals powerful outflows of gas being driven away from the black hole at tremendous velocities. These outflows are a signature of intense accretion activity. By measuring the properties of these winds and the luminosity of the system, astronomers can estimate how rapidly the black hole is consuming matter. For LID 568, these calculations suggest it is feeding at a rate approximately 40 times its Eddington limit. This finding is remarkable because it challenges the theoretical framework that defines the Eddington limit. That limit is not supposed to be merely a guideline or typical rate. It is supposed to represent a physical barrier rising from the balance between gravity and radiation pressure. When matter falls toward a black hole and gets heated to extreme temperatures, it radiates energy. This radiation pushes outward on any additional matter trying to fall in. At the Eddington limit, these two forces balance, and it should become impossible for the black hole to consume matter any faster. Yet LID 568 appears to be doing exactly that. One possible explanation involves the geometry of the accretion flow. If matter is falling toward the black hole primarily from certain directions rather than symmetrically from all sides, the radiation produced might be beamed in specific directions rather than pushing back uniformly on all incoming material. This could potentially allow feeding rates to exceed the nominal Eddington limit without violating fundamental physics. Another possibility is that our understanding of accretion physics in extreme environments remains incomplete. The Eddington limit is calculated based on certain assumptions about how matter behaves under intense radiation and gravitational fields. In the extreme conditions near a rapidly feeding supermassive black hole, effects that are usually negligible might become important. Magnetic fields, for instance, could help channel matter toward the black hole along particular paths where radiation pressure is less effective at blocking accretion. Whatever the detailed mechanism, the existence of objects like LID 568 demonstrates that at least some early black holes found ways to grow faster than conventional models allow. If super-Eddington accretion was common in the early universe, it would help explain how black holes reach such large masses in the limited time available. However, it remains unclear whether LID 568 represents a typical phase that many black holes experienced, or whether it is an unusually extreme example of a rare phenomenon. The mass of LID 568's central black hole is estimated at approximately 7.2 million solar masses. This is substantial but not extraordinarily large compared to some of the other early black holes James Webb has discovered. What makes LID 568 significant is that it provides direct observational evidence that super-Eddington growth actually occurs, not just in theoretical models but in the real universe. If this black hole has been feeding at 40 times its Eddington limit for a sustained period, it could have started from a much smaller seed than conventional scenarios would require. Researchers have modeled what might happen if a black hole with an initial mass of just 100 times the Sun underwent a brief period of super-Eddington accretion. Even a relatively short episode lasting a few million years could increase the black hole's mass by factors of hundreds or thousands. This opens the possibility that at least some of the early supermassive black holes might have grown from stellar mass origins after all, provided they experienced these intense feeding phases early in their histories. Primordial seeds, while direct collapse black holes and super-Eddington accretion provide compelling pathways for rapid early growth. Another intriguing possibility reaches even further back in cosmic history. Primordial black holes, if they exist, would have formed not from collapsing stars or gas clouds but from density fluctuations in the fabric of spacetime itself during the first instant after the Big Bang. In the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion known as cosmic inflation. During this brief phase, quantum fluctuations were stretched to macroscopic scales, creating regions of space with slightly higher or lower densities than average. Most of these fluctuations were small, but in principle, there could have been rare regions where the density was high enough that gravity immediately overwhelmed outward pressure, causing the region to collapse into a black hole. The concept of primordial black holes was first proposed by Stephen Hawking in the 1970s. Hawking showed that such objects could in principle form with essentially any mass, depending on the size of the density fluctuation that created them. Tiny primordial black holes with masses less than a large asteroid would have evaporated long ago through a quantum process known as Hawking radiation. But larger primordial black holes would be stable and could persist throughout the entire history of the universe. For decades, primordial black holes remained purely theoretical, with no direct evidence for their existence. Various astronomical surveys have placed constraints on how common primordial black holes of different masses could be, ruling out scenarios where they make up a large fraction of the universe's matter. But these constraints still allow for populations of primordial black holes at certain mass ranges, and the early universe discoveries from James Webb have renewed interest in this possibility. If primordial black holes formed with masses in the range of thousands to millions of times the Sun's mass, they could serve as the seeds for early supermassive black holes. Unlike stellar mass black holes that must grow from modest origins, primordial black holes could start with an enormous advantage. A primordial black hole of 1 million solar masses, existing since the beginning of the universe, would need to grow by only a factor of a few to produce the multi-million solar mass black holes observed in galaxies like UHZ-1 or GNZ-11. One study analyzing GNZ-11 has suggested that its central black hole might have originated from the merger of multiple primordial black holes. In this scenario, primordial black holes would tend to congregate in the densest regions of the early universe, the same regions where the first galaxies were beginning to form. As these black holes encountered each other, they would merge, rapidly building up mass. Within a few 100 million years, a cluster of primordial black holes could merge into a single object millions of times more massive than the Sun. The primordial black hole hypothesis has the advantage of pushing the formation problem back to the earliest moments of the universe, where our understanding of physics becomes more uncertain and exotic possibilities are more plausible. It also potentially connects black hole formation to fundamental physics and cosmic inflation, areas where direct observational tests are extremely difficult. However, the hypothesis faces challenges. The density fluctuations required to form primordial black holes of the necessary masses require fine-tuning the conditions of the early universe in ways that may seem contrived. A related but distinct possibility involves what some researchers call not quite primordial black holes. These would have formed not in the first instant after the Big Bang but during the first few million years of cosmic history, before the first stars ignited. During this period, massive clouds of primordial hydrogen and helium gas were collapsing under their own gravity. While most of these clouds would have fragmented to form clusters of stars, under special circumstances a gas cloud might have collapsed without fragmenting, creating a massive black hole directly. Wenzerkin, a theoretical physicist at New York University, has worked on models of these not quite primordial black holes. She explains that forming primordial black holes in the first instant after the Big Bang requires extremely dense regions, which in turn requires fine-tuning parameters in cosmological models. If those constraints are relaxed slightly, dense enough regions appear somewhat later in cosmic history rather than at the very beginning. These regions could then collapse to form black holes with masses potentially ranging from thousands to millions of suns, providing excellent seeds for later supermassive black hole growth. One argument in favor of primordial or very early black hole formation comes from the chemical composition of early galaxies. Almost all elements heavier than hydrogen and helium are created through nuclear fusion in the cores of massive stars and dispersed when those stars explode as supernovae. This process of stellar nucleosynthesis takes time. The first stars had to form, live out their brief but intense lives, and die before heavy elements could be dispersed into space. Some of the early galaxies observed by James Webb show surprisingly low abundances of heavy elements, while they are not completely metal-free, indicating that some stellar generations had already occurred. The low metallicity suggests these galaxies formed very early, when few stars had yet exploded to enrich the gas. Black holes existing in these low metallicity environments could potentially have formed before or during the very first generation of stars, supporting primordial or very early direct collapse scenarios rather than formation from later. Stellar remnants. Chapter 4. The architecture of early galaxies. The discoveries of massive early black holes have implications that extend far beyond black hole formation itself. In the modern universe, supermassive black holes and their host galaxies appear to be intimately connected. Observations of nearby galaxies have revealed tight correlations between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the total mass of stars in the central bulge or the velocity dispersion of stars orbiting in the galaxy's core. These correlations suggest that black holes and galaxies co-evolve, influencing each other's growth. When a supermassive black hole feeds actively on surrounding gas, it becomes what astronomers call an active galactic nucleus. The tremendous energy released by the infalling matter can drive powerful winds that sweep through the galaxy, heating gas and potentially regulating star formation. At the same time, the galaxy funnels gas toward the black hole, enabling it to grow. Through these feedback mechanisms, the black hole and galaxy appear to regulate each other's growth, arriving at the observed correlations. But the early universe, as revealed by James Webb, does not seem to follow these rules. The black holes being discovered in ancient galaxies are disproportionately massive compared to their hosts. In UHC1, the black hole contains mass roughly equal to all the stars in its galaxy, rather than being 1,000 times smaller as in modern galaxies. In objects like QS01, there hardly seems to be a galaxy at all, just a massive black hole with at most a modest stellar population. This raises profound questions about the order of assembly in the early universe. Did black holes form first, with galaxies assembling around them later? Or did galaxies and black holes form together but through processes that initially created much more massive black holes relative to their stellar populations than we see in the modern universe? If the latter, what caused the relationship between black holes and galaxies to evolve over time toward the correlations we observe today? One possibility is that the most massive early black holes were indeed overmassive relative to their galaxies, but this situation was temporary. Over time, these galaxies continued to form stars and grow, while their central black holes may have experienced slower growth or even periods of quiescence. Eventually, after billions of years, the galaxies caught up in mass, bringing the systems into the standard relationships we observe in the nearby universe. Another intriguing possibility is that we are observing selection effects. James Webb is specifically designed to detect extremely distant, and therefore ancient, objects. The telescope might be most sensitive to finding those early galaxies that contain the brightest central black holes, even if most early galaxies did not have such disproportionate black holes. If the systems we are detecting are unusual examples rather than typical, the early universe might have been more diverse than current observations suggest. Distinguishing between these scenarios will require larger samples and more detailed observations. Programs are underway to use James Webb to conduct deeper surveys of the early universe. cataloging larger numbers of galaxies and characterizing their properties systematically by building up statistical samples rather than relying on individual spectacular examples. Astronomers hope to determine which types of early galaxies were common and which were rare. The relationship between early black holes and their surrounding gas is also coming into focus through Webb's observations. When a supermassive black hole feeds actively, the ultraviolet radiation it emits can ionize gas over enormous volumes of space surrounding the black hole. This creates distinctive spectral signatures that Webb's sensitive spectrographs can detect. By mapping these signatures, astronomers can determine the extent of the ionized regions and infer the radiation output of the central black hole. One particularly exciting recent discovery involves evidence for the epoch of reionization in progress. The epoch of reionization refers to the period when the first stars and black holes produced enough ultraviolet radiation to ionize the vast clouds of neutral hydrogen that filled intergalactic space. Before reionization, the universe was filled with opaque neutral hydrogen fog that blocked ultraviolet light. After reionization, this fog had been turned into transparent ionized plasma, allowing light to travel freely through intergalactic space. James Webb has detected galaxies showing clear signs of having created large ionized bubbles in their surroundings. A galaxy designated Jade's GSC 131, observed just 330 million years after the Big Bang, appears to be surrounded by a bubble of ionized gas carved out by radiation from its stars and central black hole. This represents one of the earliest signs of reionization yet discovered, demonstrating that the process was well underway by this early time. These observations suggest that supermassive black holes may have played a significant role in reionizing the universe. While massive stars certainly contributed ultraviolet radiation, the energy output from actively feeding black holes could have been equally or even more important. Given that James Webb is finding black holes throughout the early universe, often far more luminous than anticipated, their collective contribution to cosmic reionization may need to be reconsidered. As evidence accumulates from James Webb and other observatories, a consensus is emerging that there is unlikely to be a single mechanism responsible for all early supermassive black holes. Instead, different pathways may have operated in different environments or at different times, producing the diverse population of objects we now observe. Priyam Vadanatarajan, an astrophysicist at Yale University who has been a leading theorist in black hole formation, has advocated for this pluralistic view. She points out that the universe is a complex place where multiple processes can occur simultaneously. Some black holes might have formed through direct collapse in pristine gas clouds. Others might have originated as primordial black holes or very early direct collapses. Still, others might have grown from stellar mass origins through super-Eddington accretion or particularly favorable conditions for rapid growth. The key may lie in understanding which conditions favor which pathways. Direct collapse, for instance, requires very specific circumstances: a massive gas cloud that remains metal-free, bathed in sufficient ultraviolet radiation to prevent fragmentation, but not so much radiation that the gas is blown away entirely. These conditions might have been relatively rare, occurring only in special environments. If so, direct collapse black holes would represent only a fraction of all early supermassive black holes, but they could still be an important pathway for the most massive examples. Primordial black holes, if they exist, would have been most abundant in regions where the density of the early universe happened to be slightly higher than average. These would tend to be the same regions where galaxies formed first. This could create a situation where some early galaxies inherited primordial black hole seeds, while others formed black holes through later processes. The galaxies with primordial seeds would have a head start in building massive black holes, potentially explaining why some early galaxies have such disproportionately large black holes. Super-Eddington accretion might have been more common in the early universe than it is today. The gas in the early universe was denser and had different properties than gas in the modern universe. It was metal poor, meaning it lacked the heavy elements that can help gas radiate energy efficiently. Ironically, this could have made super-Eddington accretion easier, because the gas around a black hole would have been less effective at converting gravitational energy into radiation that could push back on incoming matter. The cocoon phase represented by the little red dots may be a universal or near-universal stage in supermassive black hole development. regardless of how a black hole initially formed, whether from direct collapse, primordial origins, or stellar mass. It might tend to go through a phase where it is surrounded by dense gas from which it feeds rapidly. During this phase, the black hole grows quickly while remaining relatively hidden from view. Once the cocoon is consumed or blown away, a much larger black hole is revealed. Ignaz Judes of Cambridge University has emphasized that understanding these different pathways is not just about cataloging mechanisms but about understanding the physical conditions in the early universe. Each formation mechanism depends on the properties of the gas, the radiation environment, the presence of dark matter, and numerous other factors. By determining which mechanisms actually operated, we learn about conditions that are otherwise difficult to probe. The interplay between these different mechanisms may have been crucial. Consider a scenario where primordial black holes with masses of thousands of suns formed from density fluctuations in the first instant after the Big Bang. These primordial seeds settle into regions of dark matter where the first galaxies will eventually form. When gas begins collapsing into these dark matter halos a few 100 million years later, it is funneled toward the primordial black holes, which begin feeding. Some of these black holes experience super accretion, rapidly growing to millions of solar masses. As they grow, they enter a cocoon phase, surrounded by dense gas from which they continue to feed. Eventually, the radiation from the growing black hole begins to influence its environment more dramatically. Powerful winds driven by the black hole's energy output start clearing away gas, both feeding the black hole and eventually limiting its growth. The black hole emerges from its cocoon as a young quasar, an intensely luminous object that cannot shine its entire host galaxy. Over time, as gas is depleted and star formation uses up available material, the quasar fades, and the black hole enters a period of slower growth, gradually coming into the mass relationship with its galaxy that we observe in the modern universe. This scenario is speculative, but it illustrates how multiple mechanisms might work together in a sequence rather than operating independently. Different observations might be catching different stages of this process, as one might represent a black hole that has emerged from its cocoon and is now a bright quasar. Little red dots might be black holes still in their cocoon phase. G and Z11 might be somewhere in between, with the cocoon partially cleared but still substantial. The broader implications. The revolution in understanding early supermassive black holes has implications that ripple through multiple areas of astrophysics and cosmology. If massive black holes existed throughout the early universe, their energy output would have profoundly influenced their surroundings. The radiation from these black holes could heat gas, preventing it from collapsing to form stars in some regions while triggering star formation in others. The powerful winds driven by black hole accretion could expel gas from galaxies entirely, enriching the intergalactic medium with heavy elements. This feedback between black holes and their environments is thought to be crucial for understanding why galaxies have the properties they do. Simulations of galaxy formation that do not include black hole feedback tend to produce galaxies that are too dense and too massive compared to observations. Including energy input from supermassive black holes helps regulate galaxy growth, preventing too much gas from turning into stars. If black holes were even more influential in the early universe than previously thought, this could help explain observed properties of early galaxies. The chemical evolution of the universe might also have been affected. Black hole accretion and the winds it drives can mix material over large volumes. If early black holes were numerous and highly active, they could have helped distribute the heavy elements produced by the first supernovae more rapidly and over larger scales than stellar processes alone would allow. This could have accelerated the chemical enrichment of the universe, enabling later generations of stars to form with higher metallicity than would otherwise be expected. Understanding early black hole formation also connects to fundamental physics and cosmology. If primordial black holes contributed significantly to early black hole populations, this tells us something about conditions in the first instant after the Big Bang and the nature of cosmic inflation. The density fluctuations that would produce primordial black holes are related to the same fluctuations that eventually produced all the structure in the universe. Studying the black hole population therefore provides an unusual window into the physics of the very early universe. There is even a speculative connection to dark matter. Primordial black holes have been proposed as one possible explanation for dark matter, the invisible substance that makes up most of the matter in the universe. While large populations of primordial black holes have been largely ruled out as dark matter candidates by various observations, it remains possible that a fraction of dark matter consists of such objects. If James Webb discoveries strengthen the case for primordial black holes in the mass range relevant for seeding supermassive black holes, it could revive interest in this connection. The findings also demonstrate the power of the James Webb Space Telescope itself. The telescope was designed with the primary science goal of studying the first galaxies and understanding how galaxies formed. The abundance of massive black holes it is discovering was not necessarily anticipated to this degree, but Webb's capabilities are perfectly suited for this work. The telescope's large mirror and sensitive infrared detectors allow it to see extremely distant and faint objects. Its spectrographs can obtain detailed spectra revealing the physical conditions in these distant systems. Future observations will continue to refine our understanding. Webb is currently executing a variety of deep survey programs targeting different areas of sky at different depths. These surveys are designed to build up statistical samples of early galaxies, allowing systematic studies of their properties. As the sample size grows, it will become possible to answer questions that individual objects cannot address. How common were massive black holes in the early universe? How does their abundance change with cosmic time? What is the distribution of black hole masses, and does it differ from what we see in the present-day universe? Other observatories will contribute complementary information. The European Space Agency's Euclid telescope, launched in 2023, is conducting a wide-area survey that will discover large numbers of distant galaxies, including many from the early universe. While Euclid cannot match Webb's sensitivity or detailed spectroscopic capabilities, its wide field of view allows it to cover much larger areas of sky, potentially finding rare objects that Webb's narrower surveys might miss. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will combine aspects of both approaches. Roman will have a field of view about 100 times larger than Webb's while still operating at infrared wavelengths suitable for studying the distant universe. It will be able to conduct both wide surveys to find rare objects and targeted deep observations of particularly interesting systems. Roman will also have advanced coronagraphic capabilities that could potentially allow direct imaging of environments around some active black holes. Ground-based facilities are also evolving. The next generation of extremely large telescopes, including the extremely large telescope being built in Chile and the 30-meter telescope planned for Hawaii, will have collecting areas far larger than Webb's. While their infrared sensitivity from the ground cannot match space-based observations, their enormous light-gathering power will enable detailed spectroscopy of even very faint objects. These facilities will be particularly valuable for studying the detailed physics of gas around black holes and the interplay between black holes and their host galaxies. Gravitational wave observatories provide a completely different window into black hole populations. The LIGO and Virgo detectors have revolutionized astronomy by detecting gravitational waves from merging black holes, mostly stellar mass objects in the nearby universe. Future space-based gravitational wave detectors, such as the proposed LISA mission, will be sensitive to lower-frequency gravitational waves produced by merging supermassive black holes. If supermassive black holes in the early universe grew in part through mergers, LISA could potentially detect the gravitational wave signals from these ancient merger events, providing direct information about black hole growth mechanisms that optical observations cannot access. The emerging picture of the early universe is one considerably richer and more complex than existed just a few years ago. Before James Webb, the conventional narrative held that the early universe was relatively simple. Primordial gas began collapsing under gravity to form the first stars, which lived, died, and left behind modest black holes that gradually grew over billions of years. Galaxies assembled gradually through the merger of smaller structures, and supermassive black holes grew in concert with their host galaxies through a relatively gentle coevolution. This narrative is not entirely wrong, but it is incomplete. The early universe now appears to have been a far more dynamic place, with multiple competing and complementary processes creating a diverse population of early galaxies and black holes. Massive black holes appeared surprisingly early, through mechanisms that remain debated but clearly involve physics beyond simple stellar evolution. These black holes profoundly influenced their environments, regulating star formation and potentially playing a major role in ionizing the universe. Some early galaxies evolved rapidly, forming large populations of stars within the first few 100 million years of cosmic history. Others were dominated by their central black holes, which outshone the surrounding stars. Still others may have been quenched early, with their star formation shut down by energy input from their black holes or other processes, leaving them as compact red systems that would evolve into some of the massive elliptical galaxies we see today. The relationships between different components of galaxies, stars, gas, dark matter, and black holes were different in the early universe than they are today. Black holes were more massive relative to their host galaxies. Gas fractions were higher, with galaxies containing more gas relative to stars than is typical in modern systems. Star formation rates were higher, with some early galaxies forming stars hundreds of times faster than the Milky Way does today. The feedback mechanisms that regulate galaxy growth were operating under different conditions than they do in the present-day universe. Understanding this early era is crucial for understanding cosmic history as a whole. The decisions made by the universe in its first billion years, what types of structures formed, how quickly they assembled, how black holes and galaxies interacted set the stage for everything that followed. The galaxies we see around us today, including our own Milky Way, are the products of processes that began in this early era. The metals in our bodies were first forged in stars that formed when the universe was young. The supermassive black hole at our galaxy's center likely traces its origins back billions of years to the same types of formation processes being revealed by James Webb. There are also practical motivations for understanding early black holes. Black hole mergers produce gravitational waves, and the rate of these mergers depends on the initial population of black holes and how they formed. Accurately predicting what gravitational wave detectors should find requires understanding how many black holes of what masses existed at different times in cosmic history. If massive black holes were far more abundant in the early universe than previously thought, this could significantly affect predictions for gravitational wave observations. The energy released by accreting black holes throughout cosmic history contributes to the overall energy budget of the universe. This energy heats gas, drives winds, produces radiation, and influences the thermal history of the intergalactic medium. Cosmological simulations that attempt to model the universe's evolution must account for black hole feedback. And the importance of this feedback depends on how massive and how active black holes were at different times. More massive and more active early black holes would mean stronger feedback, potentially changing the predicted properties of galaxies at later times. Chapter 6. The Unfinished Revolution. Despite the enormous progress enabled by James Webb, many fundamental questions remain open. We still do not know with certainty which formation mechanism or combination of mechanisms produced the first supermassive black holes. We do not fully understand why some early galaxies hosted disproportionately massive black holes while others apparently did not. We cannot yet explain why the relationships between black holes and galaxies evolved from what we see in the early universe to the tight correlations observed today. The scope of these uncertainties extends far beyond mere technical details. Each unanswered question represents a fundamental gap in our understanding of cosmic evolution. The formation mechanisms themselves remain hotly debated among theorists, with competing models each explaining some observations while struggling with others. Direct collapse scenarios can produce massive black holes quickly but require very specific conditions that may not have been common in the early universe. Primordial black holes offer an elegant solution to the timing problem but lack direct observational evidence and rely on speculative physics from the universe's first moments. Population 3 stellar collapse provides a natural pathway but faces the challenge of producing sufficiently massive seeds in the required timeframes. The mystery deepens when we consider the apparent randomness of which early galaxies hosted these massive black holes. Some observations suggest that black hole formation was not uniformly distributed across the early universe but instead followed patterns we do not yet understand. Environmental factors likely played crucial roles, with density fluctuations, gas metallicity, radiation backgrounds, and magnetic fields all potentially influencing where and when massive black holes could form. The interplay between these factors creates a complex web of causation that current models struggle to capture fully. The evolution of black hole galaxy relationships represents another layer of complexity. In the present-day universe, we observe tight correlations between central black hole masses and various galaxy properties, suggesting a co-evolutionary relationship that has persisted over billions of years. However, observations of early galaxies reveal systems where these relationships appear much looser or even absent entirely. This suggests that the coupling between black holes and their host galaxies strengthen over cosmic time through mechanisms we are only beginning to understand. The super-Eddington accretion observed in objects like LID 568 challenges theoretical understanding of how matter behaves in extreme environments. The detailed physics of how a black hole can exceed its nominal Eddington limit remains an active area of research. Understanding this process could reveal new insights into accretion physics with implications beyond just early black holes, potentially applying to other systems where matter falls onto compact objects under extreme conditions. The Eddington limit itself represents a fundamental balance between the inward pull of gravity and the outward pressure of radiation. When matter falls onto a black hole and forms an accretion disk, friction heats the material to millions of degrees, causing it to emit intense radiation. This radiation exerts pressure on surrounding matter, creating a natural feedback mechanism that should theoretically limit how fast a black hole can grow. For a black hole to exceed this limit suggests either that our understanding of accretion physics is incomplete or that early black holes operated under different conditions than we typically assume. Several theoretical mechanisms have been proposed to explain super-Eddington accretion. Magnetic fields could channel matter directly onto the black hole while allowing radiation to escape more easily in other directions. Thick, geometrically complex accretion flows might trap radiation long enough for matter to continue falling inward despite intense heating. Dense, cold gas streams could overwhelm the radiation pressure through sheer volume. Each of these possibilities requires specific conditions and makes different predictions about what we should observe, providing testable hypotheses for future research. The implications of super-Eddington accretion extend beyond black hole formation to broader questions about galaxy evolution. If early black holes could indeed grow faster than theoretical limits suggested, this fundamentally changes how we understand the timing and pace of cosmic structure formation. It suggests that massive black holes could have influenced their environments much earlier and more dramatically than previously thought, potentially affecting star formation rates, gas distribution, and chemical enrichment across significant volumes of space. The little red dots have been identified as young black holes in cocoon phases, but many details remain unclear. How long does the cocoon phase last? What determines when a black hole enters and exits this phase? Do all early black holes go through such a stage, or only some? The answers will require both better observations and more sophisticated theoretical modeling of how gas behaves around rapidly growing black holes. The cocoon phase itself represents a critical period in black hole evolution that we are only beginning to understand. During this stage, the black hole appears to be surrounded by dense gas and dust that obscures much of its emission while potentially fueling rapid growth. The red coloration observed in these objects suggests specific physical conditions likely involving dust absorption and ray emission of light at longer wavelengths. This process requires careful energy balance between heating from accretion and cooling through radiation, creating a delicate equilibrium that determines the observable properties. The duration of the cocoon phase has profound implications for how we interpret observations. If this phase is relatively brief, lasting only millions of years, then the little red dots represent snapshots of rare transitional moments in black hole evolution. Conversely, if cocoon phases can persist for hundreds of millions of years, they might represent a common state for early black holes, fundamentally altering our estimates of black hole formation rates and growth timescales. Determining which scenario is correct requires systematic studies of large samples of early galaxies to establish the statistical frequency of red dot objects. The physical mechanisms that govern entry into and exit from cocoon phases remain poorly understood. Transitions might be triggered by changes in gas supply, either through environmental factors like galaxy mergers or internal processes like stellar feedback. Alternatively, they might represent natural evolutionary stages that all growing black holes experience, with timing determined by fundamental physics rather than external circumstances. Distinguishing between these possibilities requires detailed modeling of gas dynamics around accreting black holes under realistic early universe conditions. The connection to primordial black holes remains particularly speculative. While some researchers find the primordial black hole hypothesis attractive for explaining early massive black holes, direct evidence for primordial black holes remains elusive. Distinguishing a black hole that formed from a direct collapse a few 100 million years after the Big Bang from one that formed from a density fluctuation in the first instant after the Big Bang is extremely difficult based on observations of the black hole itself billions of years later. Novel observational strategies or theoretical insights will be needed to make progress on this question. Primordial black holes occupy a unique position in cosmological theory, representing a direct link between quantum fluctuations in the early universe and large-scale structure formation. If they exist, they would have formed during the first fraction of a second after the Big Bang, when density fluctuations exceeded critical thresholds for gravitational collapse. Unlike black holes that form from stars or direct collapse of gas clouds, primordial black holes would carry no chemical signature of their formation process, making them extraordinarily difficult to identify through conventional astronomical observations. The mass spectrum of primordial black holes depends critically on the nature of density fluctuations in the early universe, which in turn relates to fundamental physics during cosmic inflation. Different inflationary models predict different mass distributions, ranging from microscopic black holes that would have evaporated long ago through Hawking radiation to supermassive objects that could serve as seeds for the black holes we observe today. Testing these predictions requires precise measurements of both black hole masses and formation redshifts, pushing observational capabilities to their limits. Indirect evidence for primordial black holes might come from their influence on cosmic history rather than direct detection. If a significant fraction of dark matter consists of primordial black holes, they would have affected structure formation, nucleosynthesis, and the cosmic microwave background in subtle but potentially detectable ways. Conversely, if massive primordial black holes served as seeds for supermassive black holes, their existence might be inferred from statistical studies of black hole populations and their correlation with large-scale structure. The observational challenges in identifying primordial black holes highlight broader issues in connecting theoretical models with astronomical data. Many fundamental questions about the early universe involve physics beyond the standard model, operating under conditions that cannot be reproduced in laboratory experiments. Distinguishing between competing theoretical scenarios often requires extremely precise measurements of subtle effects, demanding both technological advances and innovative analysis techniques. There is also the question of how representative the objects discovered so far are of the early universe as a whole. James Webb observes only tiny patches of sky in detail, and even its widest surveys cover only a small fraction of the observable universe. It is possible that the most dramatic objects being discovered represent unusual extremes rather than typical conditions. Building up large enough statistical samples to determine what was normal versus rare in the early universe will require continued observations over many years. The sampling challenges inherent in deep field observations create fundamental limitations in our ability to characterize early universe populations. Each James Webb Deep Field covers an area smaller than the Moon as seen from Earth, representing roughly 1/13 millionth of the entire sky. While these fields are chosen to be representative of average cosmic conditions, the universe is inherently inhomogeneous, with significant variations in galaxy density, star formation activity, and environmental conditions across different regions. The brightest and most massive objects detected in these surveys are by definition the most extreme examples of their class. Selection effects favor the discovery of unusually active black holes and the most luminous galaxies, potentially creating a biased view of typical early universe conditions. More common but fainter objects may remain undetected, hidden below the sensitivity thresholds of even the most sophisticated instruments. Understanding the true demographics of early black holes and galaxies requires careful accounting for these observational biases. Statistical studies of early universe populations face additional challenges from cosmic variance, the natural fluctuation in object densities across different regions of space. Early surveys of small areas might accidentally sample regions that are unusually dense or sparse in galaxies, leading to incorrect conclusions about overall formation rates. Overcoming these limitations requires observations of multiple independent fields and sophisticated statistical techniques to extract robust population characteristics from limited data. The temporal dimension adds another layer of complexity to population studies. The early universe was evolving rapidly, with significant changes in conditions occurring over timescales of hundreds of millions of years. Objects observed at slightly different redshifts sample different evolutionary stages, making it challenging to distinguish genuine diversity in formation mechanisms from simple evolutionary progression. Disentangling these effects requires both broader samples and more sophisticated models of how black hole and galaxy properties change with time. Theoretical work is proceeding in parallel with observations. Astrophysicists are developing increasingly sophisticated computer simulations of the early universe, attempting to model the processes of star formation, black hole growth, and galaxy assembly in a realistic way. These simulations must incorporate complex physics including gas dynamics, radiative transfer, magnetic fields, stellar evolution, and black hole accretion. As computing power increases and simulation techniques improve, these models become more realistic and can make increasingly detailed predictions to compare with observations. The computational challenges in simulating early universe conditions are staggering. Modeling galaxy formation requires following the gravitational evolution of dark matter, the hydrodynamics of gas flows, the thermodynamics of heating and cooling processes, the formation and evolution of stars, and the feedback effects of supernovae and black hole accretion. Each of these processes operates on different spatial and temporal scales, creating a multi-scale problem of extraordinary complexity. Modern simulations employ sophisticated numerical techniques to handle this complexity. Adaptive mesh refinement allows computational resources to be concentrated in regions where the highest resolution is needed. Smooth particle hydrodynamics provides a natural framework for following gas flows in three-dimensional space. Monte Carlo methods enable realistic modeling of radiative transfer through dusty environments. Subgrid models parameterize processes that occur below the resolution limit but have important macroscopic effects. Despite these advances, fundamental limitations remain. No simulation can currently follow all relevant physics at all scales simultaneously. Choices must be made about which processes to include and how to parameterize their effects. Different simulation codes make different approximations, sometimes leading to different predictions even when starting from the same initial conditions. Understanding which differences matter and which are artifacts of numerical implementation requires careful cross-validation between different approaches. The treatment of black hole formation and growth in simulations presents particular challenges. The actual formation event involves physics at scales far below what can be resolved in cosmological simulations. Instead, black holes are typically inserted when certain conditions are met, and their subsequent evolution is modeled using parameterized prescriptions for accretion and feedback. The validity of these prescriptions depends critically on smaller scale simulations and theoretical understanding that is still evolving. One challenge for simulations is incorporating the wide range of physical scales involved. A simulation of early galaxy formation must follow processes operating on scales from individual stars or even smaller for black hole accretion up to entire galaxy clusters spanning millions of light years. This dynamic range is difficult to capture in a single simulation. Different research groups take different approaches, either focusing on detailed modeling of small regions or attempting larger-scale simulations that capture the broader context but must simplify small-scale processes. The scale separation problem in astrophysical simulations reflects fundamental limitations in current computational approaches. A full-resolution simulation of galaxy formation would need to resolve individual stellar birth clouds while simultaneously tracking cosmic structure formation over billions of light-years, a dynamic range of more than 20 orders of magnitude. Current technology cannot approach this level of detail, forcing researchers to make strategic choices about which scales to prioritize. Zoom-in simulations attempt to bridge these scales by starting with large cosmological volumes and progressively increasing resolution in regions of interest. This approach allows detailed study of individual galaxy formation while maintaining realistic boundary conditions from the larger scale environment. However, these simulations are computationally expensive and can only examine small numbers of objects, limiting their ability to establish general principles about early universe evolution. Large volume simulations take the opposite approach, modeling vast regions of the universe at moderate resolution to capture the full diversity of cosmic environments. These simulations excel at predicting statistical properties of galaxy populations and their spatial distribution but struggle with detailed physics of individual objects. The challenge lies in developing subgrid models that accurately represent small-scale processes based on resolved quantities. Recent advances in computing have enabled hybrid approaches that combine the strengths of both strategies. Simulation suites now model multiple realizations of cosmic volumes at different resolutions, allowing researchers to study both detailed individual object evolution and population-wide statistics. Machine learning techniques are being developed to bridge scales more effectively, using high-resolution simulations to train models that can be applied in lower-resolution contexts. Comparing simulations with observations also requires careful thought about what observables to compare. We cannot directly observe most of the properties of early galaxies. Instead, we see their light filtered through billions of years of cosmic expansion and scattered by intervening matter. Simulations must be post-processed to predict what observers would actually see, accounting for these effects. Discrepancies between simulation predictions and observations could indicate problems with the simulations, but they could also indicate issues with how the observables are interpreted. The process of creating synthetic observations from simulation data involves sophisticated radiative transfer calculations that account for dust absorption, stellar population synthesis, and cosmological effects. Each step introduces uncertainties and approximations that can significantly affect the predicted observables. Dust models must account for grain size distributions, chemical composition, and spatial distribution within galaxies. Stellar population models require understanding of stellar evolution, supernova rates, and chemical enrichment histories. Instrumental effects add another layer of complexity to simulation observation comparisons. Real telescopes have finite resolution, sensitivity limits, and wavelength-dependent responses that must be incorporated into synthetic observations. The process of detecting and characterizing objects in simulated images must mirror the procedures used on real data to enable fair comparisons. Systematic differences in analysis techniques can lead to apparent discrepancies that reflect methodology rather than genuine physical disagreements. The interpretation of observational data itself involves model-dependent assumptions that may not be fully appreciated. Measuring galaxy masses, star formation rates, and black hole accretion rates from photometric and spectroscopic observations requires translating observed quantities through theoretical frameworks that may be incomplete or incorrect. When simulations disagree with observations, the fault may lie with the simulation physics, the observational analysis, or the theoretical framework connecting them. These challenges highlight the iterative nature of progress in theoretical astrophysics. Discrepancies between simulations and observations drive improvements in both modeling techniques and observational analysis. As simulations become more sophisticated, they make increasingly detailed predictions that can be tested against observations. Conversely, unexpected observational results motivate new simulation experiments designed to understand their physical origins. The revolution in understanding early supermassive black holes is far from complete. If anything, the pace of discovery is accelerating as more data becomes available and analysis techniques improve. James Webb is still early in what is expected to be a multi-decade mission. The telescope has only begun to scratch the surface of what it will eventually reveal about the early universe. Each new deep survey, each improved spectroscopic analysis, each novel observational technique has the potential to uncover new surprises. The technological capabilities of James Webb continue to exceed initial expectations in many areas. The telescope's mirrors have maintained their precision better than anticipated. Its instruments have proven more sensitive than design specifications. And its operational procedures have been refined to maximize scientific efficiency. These improvements translate directly into enhanced discovery potential, enabling observations of fainter objects at greater distances than originally planned. The mission timeline for James Webb allows for continuous improvement in both observational techniques and data analysis methods. Early observations served as proof of concept studies that demonstrated instrumental capabilities and identified optimal observing strategies. Subsequent surveys have built on these lessons too. Design more efficient and comprehensive programs. Future observations will leverage accumulated experience to push even deeper into unexplored parameter space. The development of new analysis techniques specifically tailored for James Webb data has accelerated discovery rates beyond initial projections. Machine learning algorithms trained on simulation data can now identify candidate high redshift galaxies and black holes with unprecedented efficiency, improve spectroscopic reduction procedures, extract more information from the same observations. Advanced image processing techniques reveal faint structures previously hidden in noise. The synergy between James Webb and other contemporary observatories multiplies the scientific impact of each mission. Ground-based telescopes provide complementary wavelength coverage and can monitor variability in objects discovered by space observations. Radio telescopes probe different physical processes in the same systems. Gravitational wave detectors offer entirely independent constraints on black hole populations. The combination provides a multi-messenger view of early universe evolution. The collaboration between observations and theory will be crucial for continued progress. Observations reveal what the universe actually did, but theory is needed to understand why. When observations reveal something unexpected, theorists must develop new models to explain it. These models then make predictions for what else should be observed, guiding the next generation of observations. This iterative process, repeated over time, gradually converges on a deeper understanding of nature. The symbiotic relationship between observation and theory in modern astrophysics has reached unprecedented sophistication. Theoretical models now make sufficiently detailed predictions to guide specific observational programs, while observations provide constraints precise enough to distinguish between competing theoretical scenarios. This tight coupling accelerates progress by focusing both observational and theoretical efforts on the most scientifically productive questions. The feedback loop between theory and observation operates on multiple timescales. Rapid turnaround theoretical work can provide immediate interpretation of new observations, identifying their broader implications and suggesting follow-up studies. Longer-term theoretical development incorporates observational constraints into comprehensive models that make predictions. For future observations, the most transformative advances often emerge when accumulated observations force fundamental revisions to theoretical frameworks. The international nature of modern astronomical research amplifies these synergies. Theoretical groups worldwide contribute different perspectives and expertise to interpreting new observations. Observational teams share data and coordinate efforts to maximize scientific return. The rapid dissemination of results through electronic publishing and conferences ensures that new discoveries quickly inform ongoing research across the global community. The study of early black holes also illustrates how different areas of astrophysics and cosmology are interconnected. Understanding black hole formation requires knowledge of stellar evolution, gas dynamics, radiation physics, and gravitational dynamics. The effects of black holes on their environments connect to galaxy formation, chemical evolution, and cosmic reionization. Tracing black holes back to primordial origins invokes physics from the very beginning of the universe. Progress in understanding black holes therefore both depends on and contributes to progress across the field. The interdisciplinary nature of early black hole research spans scales from quantum mechanics to cosmology. Understanding accretion requires plasma physics and magnetohydrodynamics. Modeling stellar evolution demands nuclear physics and equation of state calculations. Connecting to primordial density fluctuations involves particle physics and quantum field theory. Synthesis of knowledge across these disparate fields creates both opportunities and challenges for researchers. There is something humbling about the recognition that supermassive black holes have existed throughout nearly the entire history of the universe. These objects have been part of cosmic structure since an epoch we can barely observe, long before our sun, our solar system, or our galaxy as we know it existed. The black hole at the center of the Milky Way, which human astronomers first detected only in the late 20th century, has been there for billions of years, silently orbiting along with its retinue of stars. Itself a relic from an era when the universe was young and wild and very different from the cosmos we inhabit today. This temporal perspective transforms our understanding of cosmic evolution from a linear progression to a complex symphony where different movements occur simultaneously across vast scales. While we experience the universe as mature and relatively stable, the early epochs were characterized by rapid change and extreme conditions. The black holes we observe today are survivors from that chaotic era, carrying within their properties the signatures of formation processes that may never occur again. The longevity of black holes compared to other astronomical objects provides unique windows into cosmic history. Stars are born and die on timescales of millions to billions of years. Galaxies merge and evolve continuously. But black holes persist essentially unchanged once formed, serving as fossil records of the conditions that created them. Their masses, spins, and spatial distributions preserve information about early universe physics long after other traces have been erased. The discovery that black holes formed so early and grew so massive also speaks to the power and limitations of human knowledge. For decades, astronomers developed what they thought was a solid understanding of black hole formation based on the best available observations and theoretical reasoning. That understanding was not wrong for the systems it was based on, but it was incomplete. The early universe operated under different rules, or at least emphasizing different pathways than what dominates today. Only by building instruments capable of observing that early universe directly could we discover these differences. This pattern recurs throughout the history of astronomy. Each time we develop the capability to observe the universe in a new way through larger telescopes, at different wavelengths, with better instruments we discover phenomena that challenge existing theories and expand our understanding. Radio astronomy revealed quasars and pulsars, X-ray astronomy uncovered stellar mass black holes and neutron stars, gravitational wave astronomy opened a completely new window on black hole mergers. The James Webb Space Telescope continues this tradition, revealing an early universe richer and stranger than anticipated. Take different approaches, either focusing on detailed modeling of small regions or attempting larger-scale simulations that capture the broader context but must simplify small-scale processes. The scale separation problem in astrophysical simulations reflects fundamental limitations in current computational approaches. A full-resolution simulation of galaxy formation would need to resolve individual stellar birth clouds while simultaneously tracking cosmic structure formation over billions of light-years, a dynamic range of more than 20 orders of magnitude. Current technology cannot approach this level of detail, forcing researchers to make strategic choices about which scales to prioritize. Zoom-in simulations attempt to bridge these scales by starting with large cosmological volumes and progressively increasing resolution in regions of interest. This approach allows detailed study of individual galaxy formation while maintaining realistic boundary conditions from the larger scale environment. However, these simulations are computationally expensive and can only examine small numbers of objects, limiting their ability to establish general principles about early universe evolution. Large volume simulations take the opposite approach, modeling vast regions of the universe at moderate resolution to capture the full diversity of cosmic environments. These simulations excel at predicting statistical properties of galaxy populations and their spatial distribution, but struggle with detailed physics of individual objects. The challenge lies in developing subgrid models that accurately represent small-scale processes based on resolved quantities. Recent advances in computing have enabled hybrid approaches that combine the strengths of both strategies. Simulation suites now model multiple realizations of cosmic volumes at different resolutions, allowing researchers to study both detailed individual object evolution and population-wide statistics. Machine learning techniques are being developed to bridge scales more effectively, using high-resolution simulations to train models that can be applied in lower-resolution contexts. Comparing simulations with observations also requires careful thought about what observables to compare. We cannot directly observe most of the properties of early galaxies. Instead, we see their light filtered through billions of years of cosmic expansion and scattered by intervening matter. Simulations must be post-processed to predict what observers would actually see, accounting for these effects. Discrepancies between simulation predictions and observations could indicate problems with the simulations, but they could also indicate issues with how the observables are interpreted. The process of creating synthetic observations from simulation data involves sophisticated radiative transfer calculations that account for dust absorption, stellar population synthesis, and cosmological effects. Each step introduces uncertainties and approximations that can significantly affect the predicted observables. Dust models must account for grain size distributions, chemical composition, and spatial distribution within galaxies. Stellar population models require understanding of stellar evolution, supernova rates, and chemical enrichment histories. Instrumental effects add another layer of complexity to simulation observation comparisons. Real telescopes have finite resolution, sensitivity limits, and wavelength-dependent responses that must be incorporated into synthetic observations. The process of detecting and characterizing objects in simulated images must mirror the procedures used on real data to enable fair comparisons. Systematic differences in analysis techniques can lead to apparent discrepancies that reflect methodology rather than genuine physical disagreements. The interpretation of observational data itself involves model-dependent assumptions that may not be fully appreciated. Measuring galaxy masses, star formation rates, and black hole accretion rates from photometric and spectroscopic observations requires translating observed quantities through theoretical frameworks that may be incomplete or incorrect. When simulations disagree with observations, the fault may lie with the simulation physics, the observational analysis, or the theoretical framework connecting them. These challenges highlight the iterative nature of progress in theoretical astrophysics. Discrepancies between simulations and observations drive improvements in both modeling techniques and observational analysis. As simulations become more sophisticated, they make increasingly detailed predictions that can be tested against observations. Conversely, unexpected observational results motivate new simulation experiments designed to understand their physical origins. The revolution in understanding early supermassive black holes is far from complete. If anything, the pace of discovery is accelerating as more data becomes available and analysis techniques improve. James Webb is still early in what is expected to be a multi-decade mission. The telescope has only begun to scratch the surface of what it will eventually reveal about the early universe. Each new deep survey, each improved spectroscopic analysis, each novel observational technique has